The main question of this talk is, how do linguistically meaningful representations emerge in deep neural networks trained from speech, so from raw speech data in an unsupervised manner? I'm going to propose a technique for wug-testing unsupervised deep learning models trained on speech. And we're going to look into a process in speech that is called reduplication, or it can also be called copying, that is very computationally complex and has been at the center of the debate between symbolic and connectionist approaches to language. And we're going to talk about how this fits into a bigger picture question where we want to build representations of higher level linguistic units such as morphology, syntax, or lexical semantics from raw speech. The central debate that this paper touches on is the debate between symbolism and connectionism, or symbolic versus connectionist approaches to language. And reduplication or copying has been at the center of this debate for a long time. So the big picture question of this paper is whether symbolic-like, rule-like representations can self-emerge in deep neural networks if we train them on raw speech in an unsupervised manner. And we want to look at three hallmarks or three main aspects of symbolic-like, rule-like representations, which is discreteness of representations, so discrete versus disentangled versus distributed representations in the models. We want to look at how we can get causality between individual units in deep neural networks and linguistically meaningful units in the output. And we want to look at whether we can get categorical outputs, because categoricity has one of the advantages of symbolic representation approaches, and connectionist approaches have traditionally have problems with categoricity of outputs. So reduplication is a more phonological process where phonological content, phonemes, get copied from a word with some added meaning. This is directly from the paper. For example, I can take pula, a string of 4 phonemes, and I copy the first 2 phonemes and get the output pupula, which would have some added meaning, maybe plurality, maybe iterativity, and so on. Okay, so this type of modeling goes back to a proposal in my proposal from 2020, that phonological and phonetic grammar or acquisition can be modeled as a dependency between the latent space and generated data in deep convolutional generative adversarial networks. So what are generative adversarial network? It's a network where you have a generator that takes some latent space and produces data. And then you have the discriminator that needs to figure out what is real and what is fake. So I propose a modification of the main architecture that is appropriate for a modeling a lexical learning or other processes in language. So how does this look like? So the idea is that the generator not only takes some noise, uniformly distributed Z variables, but also so-called code or binary code or one hot vector, okay? And so instead of having only the discriminator, I introduced the so-called Q network. It's a separate network, unlike in most other proposals. And so the generator starts learning to produce data. Now this data goes to the discriminator, right? That gets both real and fake data, or real or generated data, and needs to discriminate between those two. But it also goes into the Q network, okay? Now the Q network's role is to learn hidden latent code of the generator, okay? So it needs to take audio input and figure out which code, which unique information, which unique vector the generator had when it produced this output, okay? So in this particular architecture, lexical learning emerges, for example, completely on its own, only by the requirement of the generator to produce informative data, okay? So the Q network is the one that forces the generator into producing data that is informative. This is a little bit more schematic. We take 98 random variables distributed uniformly. This is basically noise. And we take one hot vector with 0, 1, or 1, 0. And the generator needs to produce data. The discriminator needs to figure out what is real and what is fake. The Q network needs to figure out which unique code did the generator have when it was producing this particular data. And so because our training data is such that we feed the network unpaired, unreduplicated, and reduplicated words, the most informative way to encode 0, 1, and 1, 0, to encode some meaning, some information into raw audio, is to associate 0, 1 with reduplicated or vice versa, and 1, 0 with unreduplicated or vice versa. So we train it on unpaired, reduplicated, and unreduplicated words. For example, pula, pupula, mai, mai. And this is how we constructed our data. We have ciwCW as unreduplicated and reduplication ciwCW. So for example, tara, titara, dira, didira, nira, nira, and so on. But crucially, we withheld cicira. So we did have unreduplicated cira. I'll tell you in a minute why, but we withheld the cicira reduplication pattern. So cira was always unreduplicated in the training data. Okay, so first thing we can check is whether reduplication was learned in observed data. So we can go back and then generate data. And so, for example, for code 1.0, when we generate with the code 1.0, the network outputs about 22% of unreduplicated and about 78% of reduplicated outputs. If it's the opposite code, 0.1, it's about 60%. Now, in line with Beguš 2020, we learned that you can stretch these latent variables or manipulate them outside of the training range to get a real underlying value of these code variables. And so if we generate at 5.0 code, if they want hot encoding, we get near categorical outputs of bare unreduplicated form. And if we switch the code to 0.5, we get 87%, so a high percent of reduplicated forms. So we can stretch the latent variables to outside of the training range. So in training, the network got 0 and 1, 1 or 0, and in the generation phase, we can manipulate them to outside of training range to see the underlying value of each code. So what the network encoded in each code. And so we see that the network not only encodes reduplication, it encodes when we interpolate from 1.0 to 0.1, we observe a causal effect between these code variables and the output in the generator network. For example, we see that if we interpolate from 1.0, which is unreduplicated, towards 0.1, which is reduplicated, we see the amplitude of the reduplicated syllable just attenuates until it's gone from the output, right? We see two examples here, and we can listen to them. What else can we test? How does this learning of reduplication extend to novel unobserved data? So what can we do? We can force two things in the output, right? We can force the presence of reduplication and the presence of S using a technique proposed in one of my papers where we identify variables in the network that correspond to some linguistically meaningful unit and then force them by manipulating latent space variables outside of the training range. Okay, so when we force the reduplication and S simultaneously in the output, we get clear reduplication of S initial word forms, right? So you see nice period of frication noise characteristic of S disrupted by a reduplicative syllable. For example, the first one is the generated output from the generative network when it never saw reduplicated S initial forms. The second is human recording of a reduplicated form that was never part of training data. And you can hear that they look remarkably similar. And if you look at the spectrograms or the waveforms, you see a clear pattern of S initial reduplication. Another example. Okay. So the paper includes also a couple of other experiments, for example, where we train reduplication on BearGAN architecture without this inductive bias towards discretized representation or towards informative data, producing informative data. And we see that the reduplication is replicated in those models as well. We use the same techniques, identify how the network represents reduplication, how the network represents presence of S, force them simultaneously in the output, and observe, again, reduplicated forms, even though the network never saw the reduplicated forms. Okay, so what do we learn from this? First, grammar or language acquisition can be modeled in an unsupervised way from raw speech using convolutional neural networks in the generative adversarial network framework. We saw that we can basically wug-test any process, not only reduplication, but using the technique where you force two proper linguistic properties in the output by manipulating latent variables to ranges outside of training range, we can observe their interaction and see how rule-like representations emerge in deep neural networks. We see that we have now a model that learns the linguistically meaningful units only from the requirement to output informative data, right? The network learns to encode some representation of the reduplication, right? So it assigns some unique information to reduplication in the forms of a one-hot vector, only from the requirement to output informative data. And reduplication is not only a phonological process, it's a morphophonological process. And we add the meaning component in the sense of one-hot encoding. So we can now build higher level of representations and test how syntax, basic syntactic properties or basic morphological properties can be encoded from raw speech or can be learned from raw speech in an unsupervised manner. And finally, we saw evidence for three aspects, for three properties of rule-like representations that self-emerge in these neural networks, right? We saw discretized representation because the network uses basically only two variables. And if you test how the network learns the presence of S, it basically also learns only one variable. Especially in the Bear-GAN architecture, we see a steep drop between a single latent variable that corresponds to, say, reduplication and the rest of the latent space. We saw causality. We can basically interpolate latent variables, and that has a direct effect of reduplication, a process as complex as reduplication in the output. And we saw that we can, by manipulating latent variables to extreme values, we can get near categorical outputs. And all of these three things are characteristic of rule-like, symbolic-like representation. So a few references, and thank you for your attention.